Welcome, Calculus AB. This is 6-2 differential equations, growth and decay. Let's go. So just a reminder, this is how to solve a differential equation. When I solve one, I have to remove the differential parts, so no y primes or dy dx's. Alright, so let's take this example. If I say y prime equals 2x and say solve it, what I'm going to do is integrate both sides. So you do this on both sides, so integral of y prime is just going to be y, and antiderivative of 2x is going to be x squared plus c. Alright, cool. So you've done this before. Basically find the integral of 2x. Now, let's solve a general differential equation that has x's and y's in it. So this is what you want to do, and this is going to pop up in the next few sections. This is the way I do this. So I change a y prime to dy dx. So change that to dy dx equals 2x over y. Now, in the whole goal here to actually solve this is we want to rewrite it so that the y is on one side and the x is on the other. And that includes dy and dx's. So I have this, I want to put, let's say I put the y's on this side. So what I'm going to do is I'm going to multiply by y on both sides. And then that'll cancel out, and I get y dy dx equals 2x. And then I say I don't want that dx over there, so I'm going to multiply both sides by not 2x, dx and dx. And these will cancel out, and I get y dy equals 2x dx. Now I'm going to integrate both sides. When you have the y's and the dy's and you integrate, just do the little s thingy. Since we're integrating with respect to dy, when you're just y, you just treat it like you don't do any special weird things with that. So integral of that's going to be y squared over 2, and then equals 2x. That's going to be x squared. And we can say plus c. We have to have the c on one side or the other. Doesn't matter. So my general solution is y squared over 2 equals x squared plus c. Cool. Now, and we can rewrite that equation. This is how the book did this. And they did a similar thing. They don't switch to dy dx. I'm just showing this to you. But the way they make it work is from this step, they say, oh, well, dy equals y prime dx. It's doing the same work, so if you want to do it their way, that's fine. And then they got the same solution. Now, they set the c by itself, but you don't have to do that. You can just leave it like it was. All right, so we say this. We're going to actually start applying this knowledge to other problems, and this is growth and decay. So growth and decay. You've done growth problems. Maybe you remember, maybe you don't, like interest rate problems. But so with the growth problem, the rate of change is proportional to y. So when we say proportional, it's like it's always going to be like it's going to not necessarily equal, but it's going to look like this. Your dy dx, which is your rate of change, it's going to equal y, but you can have a constant k. So it'll stay proportional with respect to this like k constant. But you know, if this one goes up, dy dt, y is going to go up. If this one goes down, y is going to go down. But we still have that proportional k. Now, what if I took that equation and I want to find the general solution? So it's dy dt, so changing over time. Again, I want to isolate variables to one side or the other. So I'm going to say, let's divide by that y on both sides. And then we're going to multiply by dt on both sides. So divide by y and multiply by dt. Oops, not dx. dt over and then over y. So what happens here is these y's cancel out and these dt's cancel out. So you get dy over y equals k dt. Okay, so let's integrate both these sides. So when you do this, that's basically 1 over y dy, and the antiderivative of 1 over y is ln of y. And then antiderivative of a constant dt is just going to be kt. And then we have a plus c. But I want to solve for y. I want to rearrange this. Oops. So I'm going to exponent. I'm going to e both sides. E to the power. You can do this. This is legal. So when you e a ln, if you remember your log rules, this just becomes y. And then we get e to the kt plus c. Now, I'm going to break up that plus c. If you remember your exponent rules, when you're summing things, I can break that up to e to the kt times e to the c power. And since e to the c power is just some constant, I can rewrite this as not just e to the c, because it's just going to be a constant anyway. So I'm going to write this as c times e to the kt. And if you're familiar with this, this might have been your exponential growth and decay. You might have seen a formula similar like this. In fact, this is our exponential growth and decay model. This is kind of the calculus way of saying this. You might have seen this as interest rate type problems. Sometimes it's a amount equals your principal times e to the RT. This was continuously compounding interest. It's the same kind of principle right here. So C is your initial value, and then K is just some constant that controls the proportionality. So how does this apply to something? Well, let's take this example here. If the rate of change of y is proportional to y, when t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? So to do this, since I give you this hint right here, the rate of change is proportional to y. That means I get to use that equation, y equals c times e to the kt. It's because that's the differential version of that was what we said before, dy dt equals kt, but we know how to write the equation now. So we got to figure out what c is, and then I got to figure out what k equals. So I got two cases right here. When time equals 0, y equals 2. In fact, so I can write that as an ordered pair. Ugh, what did I just do right there? I don't know what I did. I moved it all. Oh, well. There we go. Okay, so when t equals 0, y equals 2. So I'm going to plug that in for this first case. So 2 for y equals c times e to the k times 0, which is just going to be e to the 0. So 2, and then e to the 0 is 1, so 2 equals c. So c equals 2. c equals 2. Now, I know what c equals, I got to figure out k. So to figure out k, I'm going to substitute in that second. When time equals 2, y equals 4. And I already know what c is, so I can say let's go with 4 equals 2 times e to the k times 2, or 2k. Alright, so let's do some math here. Divide by 2 on both sides, I will get 2 equals e to the 2k. And this is where you can use some logs if you want to do this, or convert to, I'm going to ln both sides of the equation. So ln of 2 and ln of 2. When you ln an exponent e, that becomes 2k. So ln of 2 equals 2k. And then I can say k equals ln of 2 divided by 2. And we might actually want a number, so this is where you'd have to plug it into a calculator. Mine doesn't work. So this is where we plug it into a calculator. And I find my calculator. Oh well. Alright, there's my calculator. So if I want to plug that in, ln of 2 divided by 2, I will get 0.347. I'm going to round that up to 3 decimals. So 0.347. Cool. That's what my k equals. So now that I have my full equation, I can write it as, I'm going to write it over here on this side. I can say y equals c, which is 2, e to the 0.347 times t. And what is the value of y when t equals 3? So you just plug that in. So y equals 2 times e to the 0.347 times 3. And if you plug that into a calculator, you will get what's on the next page. 5.637. And this is actually a graph that modeled that. So this is an exponential function. If you remember, it kind of goes to the asymptote, never touches. So 0, 2, 2, 4, and 3, 5.67. So there we go. Now I'm going to do this Newton law of cooling in class, because that's enough notes. See ya.